Welcome to the Sobi School of Business. In this video, we will take a look at the F-test for two population variances. The circumstance that requires that we do such an F-test has to do with the assumption that we make whenever we're going to do a t-test for the difference between two population means. We usually make three assumptions. One is that the populations are normally distributed. The second assumption is that the population variances are the same. And the third assumption is that the samples are independently and randomly chosen. To test the assumption of equality of variances, we can do an F-test. And that F-test would allow us to determine whether or not we can go ahead with a t-test for the difference between two population means using the assumption of equal variances. So the learning outcome that is for this particular video is for us to become familiar with this particular F-test. Is there a test that we can perform that would allow us to test that assumption? So the principal learning outcome for this short video is to allow us to carry out the hypothesis test for the difference between two population variances. So just to reiterate our question, when we conduct a t-test for the difference between two population means with the population standard deviations unknown, we assume that these variances, and remember that standard deviation is just the square root of the variance, that these variances are equal. Is there a way to test whether or not the population standard deviations or the population variances differ? So as I go through the lecture, I want you to keep in mind a couple of questions. So you could try to answer those so that you could then check later on to see if you got it correct. The first question, the F distribution is used to test whether two sample variances are equal. True or false? Second question, in a hypothesis test involving two population variances, if the null hypothesis states that the two variances are strictly equal, then the test statistic is a chi-square statistic. True or false? In a two-tailed hypothesis test for the difference between two population variances, the test statistic is an F ratio formed by putting the largest sample variance in the numerator. True or false? And the last statement or question, the null hypothesis that two population variances are equal will tend to be rejected if the ratio of the sample variances from each population is substantially larger than 1.0. True or false? So you can make an attempt to answer these questions now, and then as we go through the rest of the lecture, see whether or not you made the correct choices. So here we are with two populations that we are interested in the difference between their means. And so we could test for the difference between their variances if those variances are unknown. So we could do either a one-tailed test or a two-tailed test. The two-tailed test would involve that we would want to prove HA in our research hypothesis that those variances are different. And so therefore in the null hypothesis, we would simply state that those variances are the same. If we wish, we could test whether one variance is actually higher than the other. So sigma 1 squared greater than sigma 2 squared. And we could then, in our null hypothesis, simply state the opposite, that sigma 1 squared is less than or equal to sigma 2 squared. Or you could have the reverse of that, which is that sigma 1 squared is less than sigma 2 squared. And in the null hypothesis, we just have the opposite of that. Okay? Now, the F distribution is formed from the ratio of two sample variances. So here's our F distribution. And we have the degrees of freedom associated with each of those populations. All right. So for the numerator, if we are going to observe the sample standard deviation from population 1, then the degrees of freedom would be n minus 1, n1 minus 1, sorry. And then for the denominator, which we'll call d2, the degrees of freedom would be n2 minus 1. So n1 is the sample from population 1, n2 is the sample from population 2. And then we have the sample variances S1 squared and S2 squared. So just to take a moment to, share some light on that F distribution. So far we've studied the normal distribution, studied the normal distribution, Z. We studied the T distribution, and so now we're introducing the F distribution. So the F distribution, as I mentioned, is formed from the ratio of two sample variances, S1 squared over S2 squared, or it could be S2 squared over S1 squared. It's just the ratio of those two. So if every time we generate two samples from the respective populations, so here we have mu1, mu2, we're interested in the difference between those, the unknown standard deviation, sigma 1, sigma 2. Then if we took a random sample from this one and observe S1, let's just say S1 squared, the sample variance, and then the second population observe S2 squared, then F would just be the ratio of those two. So let's just consider for now, we'll always put the large over the smaller, and let's assume, well, actually for now it doesn't really matter. We just put the ratio of one variance to the other. So if we take S1 squared over S2 squared, then we get an F distribution. What does that distribution look like? It turns out that the F distribution is actually skewed to the right. And because variances are never negative, it means all the values of F are going to be positive. All the values of F are going to be positive. And it turns out that the F distribution is a skewed distribution that looks something like this. So the values will basically vary from 0 to infinity, technically speaking. From 0 to infinity. So all the values are positive. And of course, the further we go out this way, then it means that the one variance is extremely larger than the other. So let's just say that 1.0 is here, where the two variances are the same. Then as you go towards the extreme right, then S1 squared is greater than S2 squared. As you go towards the extreme left, then S2 squared is much larger than S1 squared. So if we're looking for evidence that the two variances are different, we would look for it obviously in the tail, either here or in the tail over here. It's a different kind of tail. It's not a long tail, but so either of these extremes, right? Way to the right of 1.0 or way to the left of 1.0. And the reason why I want to get to the right or the left of 1.0 is because if the ratio is 1.0, the two variances are indeed the same. Okay? So just to recap, the F distribution is formed by the ratio of two independent chi-square variables. The F distribution is determined by its degrees of freedom. The assumptions: the populations are normally distributed. The samples are randomly and independently chosen. All right? We're not going to assume that the variances are equal, because it's basically just made from a ratio of two sample variances. However, we use that distribution to test whether or not population variances are equal or whether or not one is much larger than the other. Now, to use the F distribution table for two-tailed tests, always place the largest sample variance in the numerator. The largest sample variance in the numerator. And this will make the F value calculated 1 or greater than 1 and push the F values towards the right tail of the F distribution. For one-tailed test, examine the alternative hypothesis for the population that is predicted based on the alternative hypothesis, right? And then what you do is you manipulate the variances so that you ensure that the larger one is in the numerator. So it really doesn't matter if, for example, we want to test, let's say we want to test HA, that, say, if we were doing a test as follows, right? That sigma 1 squared is greater than sigma 2 squared. Sorry, and over here we have sigma 1 squared is less than or equal to sigma 2 squared. Now, if it turns out that our sample S2 squared is much greater than S1 squared, well, you know that it's not going to support this hypothesis that sigma 1 squared is greater than sigma 2 squared. So we could actually switch things around and say, here's what we will do. HO sigma 1 squared is greater than or equal to sigma 2 squared. But in our research hypothesis, we'll switch that to sigma 1 squared is actually less than sigma 2 squared. So what would happen now is that if it turns out that this is much greater than sigma 1, not sigma, but S1 squared, S2 squared is greater than S1 squared, then we may very well find evidence that the variance from population 2 is greater than that of population 1, which is also evidence that the variance from population 1 is not greater than the variance from population 2. So you could always look at the sample data and then just establish the hypothesis to match this relationship that we're looking for, which is that we will put the higher sample variance in the numerator. Okay. Now, to use the F table, let's just show you this very quickly. The thing about the F table, which is a little different from the T table now, is that we have these two different degrees of freedom. The numerator degrees of freedom, D1 or DF1, we'll put the values up here, 1, 2, 10, 15, 25, etc. And then D2, which will be the denominator degrees of freedom, 1, 2, 3, 4, 25, etc., etc. And so the way our table works is that if we find the combination of numerator degrees of freedom and denominator degrees of freedom at this intersection, what we will do is provide a set of areas and give you the corresponding F value for those areas. So in other words, for this point, we will say if the area is 10%, for example, let's say this was 10%, then we'll give you a particular F value, F10, F.10. Then if it were 5%, we'll give you the value for 0.05. If it were 1%, we'll give you the F value for 0.01. So for each of those areas, you will have the appropriate F value. And so there's a set of values here that matches each of the areas and a corresponding F value. So that's how our table works. And we need to just find some time to get used to how to using it. So as we go for an example, it will become a bit clearer how we use this particular table. So if we're testing the hypothesis where we have a directional test, F test, that means, for example, either the variance from population 1 is greater than population 2, as you can see in this case right here, or the variance from population 1 is less than population 2, as you can see in this case right here, then we will do a one-tailed test. And the area of the rejection region will be alpha. We will still put the larger over the smaller sample variance and look for the find a critical value and look for evidence as to whether or not the sample statistic falls in the rejection region. So here we will see, here's our requirement. If our F value is greater than F alpha, which is our critical value, we will reject the null hypothesis. In this case over here on the right, if it's a two-tailed test where we want to test whether or not the variances are equal versus they're not equal, then the rejection region in the right tail will be half of the significance level, alpha over 2. And so we will reject the null hypothesis if our F value, our observed value, falls in that rejection region. So here's our observed value. If it is greater than F alpha over 2, which is our critical value, we will definitely reject the null hypothesis. So that's essentially what it is. We're still using the very same principles from doing t-tests and z-tests. It's just that now our statistic is an F value and our critical value is an F critical. So once we understand how to find those, we will be able to conduct a hypothesis test. So just keep in mind that our observed value is just S1 squared over S2 squared, or S2 squared over S1 squared, and it all depends on which one is larger. But the critical value is our F value, alpha over 2, degrees of freedom 1, degrees of freedom 2. And that's assuming, of course, that the sample, what's in the numerator is sample 1, is sample variance from population 1. If it is the other way around, where the larger one comes from population 2, then we would simply make our critical value F alpha over 2, the D2, D1. So the degrees of freedom associated with sample 2 would be the numerator degrees of freedom. The degrees of freedom associated with sample 1 would be the numerator degrees of, denominator degrees of freedom, sorry. So again, we just need to make sure that we're consistent. So you could see in the first case here that we'll have D1 and D2. In the second case here, we will have D2 and D1. So D2 will be your numerator, D1 will be your denominator. In the first case, D1 will be your numerator. That's equal to N1 minus 1, N2 minus 1, N2 minus 1, N1 minus 1. Okay? So once we just make sure that things are aligned, we're good to go. So to summarize the steps, the hypothesis steps for two population variances: specify the population parameter of interest. In this case, the parameters are the population variances. Formulate the appropriate null and alternate hypotheses. That's step 2. Step 3, specify the level of significance, alpha. Step 4, construct the rejection region and specify the critical values to determine the critical values from the F distribution, or either Excel if you're planning on using Excel. But in an exam situation or a classroom situation, you may not have the benefit of Excel, so you want to learn how to use your table. So if you use the F table, note the degrees of freedom D1 and D2, numerator sample minus 1, denominator sample minus 2. So N1 minus 1 and 2 minus 1. Once you have those, we compute the test statistic, which is formed by the ratio of the two sample variances. Select the random samples from each population of interest. All right. Determine whether the assumptions have been satisfied and compute the test statistic. remembering to put the largest sample variance in the numerator. Reach the decision, compare the test statistic to the critical values, which we've already found, and reach a conclusion with respect to the null hypothesis. A decision, actually, with respect to the null hypothesis. It says conclusion, but that should be a decision. And then we draw the conclusion with respect to the research hypothesis, HA. Always remember that our decision is whether or not we will reject or not reject HO, the null, and our conclusion is whether or not we have evidence to support the research hypothesis, HA. We're going to take a look at a quick example, which basically states here that the transportation agency is concerned about waiting times for passengers who use the downtown transit center. Of particular interest is whether there is a difference in the standard deviations in waiting times at the two concourses A and B. So we have the data given to us, a significance level of 2% right here. Our sample size for concourse A is 25, concourse B is 31. The critical value will be based on F alpha over 2 and the degrees of freedom. We're going to come to that, but let's look at our sample values. For concourse A is 3.77, sample standard deviation. Concourse B is 4.79. So because B is large, SB is larger than SA, our ratio will end up being F SB squared over SA squared. We put the large over the smaller, which means our degrees of freedom for the numerator, D1, will be NB minus 1, and that's 31 minus 1. And for the denominator, D2, will be NA minus 1, which is 25 minus 1. So that's 30, and that's 24. So there we go, 30 and 24. When we compute our value of our test statistic, here it is right here. Our critical value for F alpha over 2, so it's F01. So our critical value, if we were to write it out properly, would be F, so it's alpha over 2, which is 0.01, but the numerator degrees of freedom is 30, and the denominator degrees of freedom is 24. So that turns out to be 2.577. Okay, so 2.577, and as you could see, our observed value is not larger than that, it's less than that value, so therefore we will have insufficient evidence that the variances are different. We will not be able to reject the null hypothesis in this case. Okay, so essentially if I draw on a diagram for you, you will be showing me that here our critical value is 2.577. This area, which is alpha over 2, 0.01, because alpha is 2%. And our critical value came up to 1.6 something. Not critical, our observed value, 1.6. I forgot what it was now. Let's see here. I'll find the exact value for you. The observed value was a little different, 1.6 something. So anyway, we could see here that this 1.6 is less than 2.577, so we're not in the rejection region. Here's our rejection region right here. So in this case, we will fail to reject the null hypothesis, and our conclusion would be that we have insufficient evidence that the population variances differ. That would be our conclusion in this case. So now here's a chance for you to go back to those questions. The F distribution is used to test whether two sample variances are equal, and the answer is true. Yes, it is. In a hypothesis test involving two population variances, if the null hypothesis states that the two two variances are strictly equal, then the test statistic is a chi-squared statistic. That's false. It is still an F statistic. And in a two-tailed hypothesis test for the difference between two population variances, the test statistic is an F ratio formed by putting the larger sample variance in the numerator. Answer is true. And the last one, the null hypothesis that two population variances are equal will tend to be rejected if the ratio of the sample variances from each population is substantially larger than 1. So since we are looking for evidence that takes us into the tail, extreme values, if we put the larger over the smaller, S1 squared over S2 squared, evidence would be values that are much larger than 1, so that answer is true. And so we'll keep that in mind. So hopefully you got those correct. If not, you could certainly review those answers. Here is another sample problem. This time this one is taken from our problem set that we use in class. An agricultural lab in Mexico is testing the effect of two types of fertilizers on the growth rate of mango seedlings. A random sample of 20 seedlings were given fertilizer A and 25 seedlings were given fertilizer B. The increase in the height of the seedlings over a 3-week period was measured and the results summarized below. Sample size 20 for fertilizer A with a mean growth of 50.5 millimeters, standard deviation of 13.2 millimeters. Then we have 25 for fertilizer B with a mean growth of 57.5 millimeters and a standard deviation of 8.5 millimeters. A statistician wants to perform a t-test to determine whether fertilizer B results in a larger mean growth rate for the seedlings over the 3-week period. To do the test, she must assume equal variances. Determine whether the assumption of equal variances is a reasonable assumption. Use a 5% significance level. So we look at this, we're being asked essentially to test the equality of variances. She has to make this assumption. So the question is this a reasonable assumption? So let's see how we would set this. So for this particular question, we would have our hypotheses. I'm going to change my ink right here. And HO, HA. We would say that the variances are the same, so the variances are equal. Versus variances differ. So they're not the same. If the variances are the same, then we could simply say that the variances from fertilizer A is equal to the variance from fertilizer B. But if they differ, then A is not equal to the variance of B. That's the first step. All right? So that's the first step. 2 is the test statistic. Test statistic is F is equal to, and this is where we must look at the sample data. So for the sample data, we have the sample variance for fertilizer A is larger than that of B. So we will put SA squared over SB squared. And the degrees of freedom, we'll call it dA, or that would be the numerator, would be 19, which is 20 minus 1, 19. And the denominator, which is for B, is 25 minus 1, which is 24. So 19, 24. That would be our test statistic. Step 3, the decision rule. With the decision rule, we would simply need to determine the F critical. So this is where we reject HO. So F critical would be F alpha over 2, because it's a two-tailed test, and the degrees of freedom are 19, 24. So alpha over 2, since alpha is 5%, so F, that's equal to F 0.025, which is half of 5%, 19, 24. Our critical value turns out to be 2.345. 2.345. We could look this up in Excel, or we certainly can look this up on the table. Now we go to step 4, the analysis. And that's one of the easy problems where the analysis is so fairly straightforward. F observed in this case would be 13.2 squared divided by 8.5 squared. It turns out that that is 2.412. And 2.412, excuse me, as you could see, is greater than a critical value of 2.345. Let's find a p-value. Well, the p-value is kind of interesting, trying to find a p-value of the F distribution. What you would have to do with, in this case, to find a p-value, is you look up the numerator was 19, denominator was 24. And then we're going to try to find the value of 2.412. So you got to look at the different areas. Remember that for each area you get an F value. So if it is 10% in the tail, you get a particular F value. If it is 5%, 2.5%, 1%, 0.005, and so forth. So you have these different values. What you got to do is to look to see where this value falls. And it turns out that this value falls between the values for 2% and, sorry, not 2%, but 1% and 2.5%. So that's what that's where it actually falls. But that is only half the p-value. Can't seem to be able to squish this. Oh, here we go. Sometimes you just got to find it at the right spot. So it turns out from our table that half the p-value, when we look up 2.412, is greater than 0.01, less than 0.025. And so therefore, that's only half the p-value. If we multiply everything by 2, we get 0.02 less than the p-value, the 0.05. So what we're seeing here is our p-value is less than the significance level. But not only that, our 2.412, which is our observed value, is greater than the critical value of 2.345. So that is an issue for us, because we will have to reject the null hypothesis and conclude that there is sufficient evidence that those two variances are not the same. So now step 5, the decision conclusion. So you simply say, since 2.412 is greater than 2.345, we must reject the null hypothesis, HO. What do we conclude? We have sufficient evidence the variances differ. Can we be wrong? Yes, we could possibly commit type 1 error. Okay, and what's the probability of type 1 error? The probability of type 1 error is our p-value. Sorry, I missed that. So here we go. That was fairly straightforward, I think, to solve an F-test for difference between variances. That test can be done in Excel and will be demonstrated in a separate video. So once again, just to summarize, the F-test for the difference between population variances is quite a useful test because it allows us to determine whether or not the assumption that we have equal variances is a reasonable assumption. If we do have two sample variances, we could actually test whether or not the population variances differ, and if we fail to support that, then we have no choice but to accept that it is a reasonable assumption that the two population variances are the same. Thank you.